Notice anything strange about this backboard? It doesn't matter where I shoot on it, the ball goes in. Look at that. How does it know? They say a magician shouldn't reveal their tricks, but this one's too cool not to show. Also, if you can't make it in with this hoop, you deserve to lose. I wrote software to figure out the most optimal backboard possible, and then I built it. This is that story. So I was talking to some friends about stupid stuff that we might build, and the idea of a backboard that always goes in no matter where you hit it came up, and everyone thought that was really stupid. Of course I laughed and said, haha, yeah, that's stupid, but the idea has stuck with me. I just can't stop thinking about how awesome would it be to see that in real life. I shoot the ball and it hits the corner and it goes into the hoop. That would be really cool. And so I put it in my bucket list. I want to see that backboard before I die. The only way I'm probably ever gonna see that backboard is if I build it. So let's do that. So in order to build it, I'd have to actually know what shape I want. To compute the optimal backboard shape requires a lot of programming, you know, nerd stuff. Now you're probably thinking, oh, Snorefest, I'm out of here. But before you leave, let me assure you, it's actually very interesting. So my goal is to compute an optimal backboard. A standard backboard as a flat sheet isn't very optimal. Balls really only go in if you hit them within a certain region. That's why they have that square on the backboard. If I take a shot from the center and I hit over here, the ball just misses. And the same is true for most other regions. And what I would like to do is to figure out what shape I can make the backboard, something like this, so that no matter where I hit it, the ball gets directed into the hoop. It's basically the same thing from the side as well. The idea is pretty simple. The hard part is figuring out the shape, especially in 3D, because it's a very complicated shape. So what I did to solve this problem is I did what's called a Monte Carlo simulation. And the idea is that you simulate a lot of shots. In my case, tens of millions of shots from all different locations in the court at all different locations on the backboard. And for every shot that I take, I figure out how would I need to change the backboard location in this spot that I'm hitting so that the ball will go into the hoop. So say I have a shot coming in like this, and it's coming in really fast. With the backboard as is, it might bounce off something like this, and it won't go in the hoop. But what I could do is at this location of the backboard, I could change it to be this angle, and it would redirect the ball down into the hoop. If you do this for an enormous number of shots from all the different locations, you can get a good idea of what shape the backboard needs to be so that the maximum number of shots go in. If you look at what I'm drawing for all these things, it really looks like it wants to be a parabolic shape. And that makes sense because satellite dishes are parabolas, and that's because they redirect all incoming electromagnetic waves or whatever to a single point. So if I have a ray coming in like this, it'll bounce to this point, same here, and for all of them. So there's a few key things to understand to get why it's designed the way that it is, and why a straight parabolic shape doesn't really work. The first is that the balls follow trajectories. When I shoot a ball in, it's coming on some curve because it's pulled down by gravity. And then the same thing happens when it bounces off the backboard. I have to account for this fact. Depending on where I hit it vertically, they'll drop different amounts. And the amount they drop is also related to the speed that they're coming in. They'll drop less if they're coming in faster. And then the other thing that matters a lot with basketball shots is where they go depends an enormous amount on the angle they're coming in. So the bounce will be some kind of reflection. If I'm coming up, it might bounce like this. But if I'm coming down, it might bounce like that. Given the difference that you can get for different shots, it seems like this shouldn't really work because if I shoot a shot like this, I need to change the angle of the backboard in a different way than if I shoot a shot like this. And it's true, you really can't support a line drive and a slow arcing shot. I had to optimize for a type of shot, and I went for kind of the average basketball shot that's arcing. Line drives are sort of a special case far out on the edge of possible shots. And even though there is this dependence on speed and incoming angle, there's a really nice thing that makes it not as bad of a problem. And that's the fact that the ball is smaller than the hoop. So for every possible bounce that a ball does, there's actually a range of bounces that will still cause it to go into the hoop. And this actually gives pretty good amount of wiggle room in terms of speed and angle that the ball comes in for a given point on the hoop, so that it'll still go in. So the real question is, who is Monte Carlo and what does he have to do with backboards? I don't actually know who Monte Carlo is. I assume he had something to do with his technique, and I'll show you how I derived a backboard using it. So what I do is I choose a random location on the court, and then I take a random shot at the backboard. Then I look at where I hit the backboard, and I figure out what I would need to change about the angle of the backboard so that the ball will go into the center of the hoop. So say I change the surface at this location and to this angle, it will bounce into the center of the hoop. Then repeat this tens of millions of times, and remember the result for every single shot. So there's a really important subtlety, which is related to the fact that any given shot has multiple bounces off the backboard that will still go in. So for this shot, this bounce will go in, this bounce will go in, this bounce will go in, and basically infinitely other bounces within this range will go in. If you look at all of these bounces, they sort of form an ellipse. So for every shot, I can keep track of this range that it would go in and what the corresponding angle changes to that location of the backboard would be that would cause it to hit those. What I'm about to say is somewhat hand-wavy, but it does make sense. If I take this angle range for all of my simulated shots and I plot them on some kind of graph, maybe this is rotation on the y-axis, this is rotation on the x-axis, and this is a shot, I can do this for tons and tons of shots for that particular location on the backboard. And what this means is that if two ellipses overlap, if I were to set the backboard to this specific rotation or this specific angle, these two shots would go in. So what you can do is find the location in this chart where the maximum number of ellipses overlap. That will be the angle to set the backboard to in that location so that the maximum number of shots goes in. That's basically it. There's a bit more to it about having smooth, continuous backboards and making sure you're only getting sort of nominal, realistic shots. So say I do this for tens of millions of shots for all the locations on the backboard, and I choose an angle for every point of the backboard surface that I want. The only remaining question is how do I turn that into a shape? So in concept, it's really not that complicated to do. So imagine this is my backboard, we're looking down at the top of it, and I calculated all of these angles that I need the backboard to be for the shots to go in. All that I need to do is figure out what shape I can bend it into so that the surface at all of these locations is those angles. Doing this in 2D is pretty easy. Doing it in 3D is actually more challenging, but what I ended up doing is a least squared fit. I was having a hard time getting an exact fit that was smooth and continuous, and that just involved solving a very big matrix. So if I do this in 3D and I get some shape, it still won't be quite the right shape. And that's because of one other important subtlety. It's kind of hard to explain, but I think I can do it. So imagine that this is my backboard and the hoop, and this is the backboard that I calculated so that all the balls would go in. You have to remember that I was using the original backboard to compute these angles. So if I have this shot and it bounces like this to go into the hoop, where this ball goes is relative to where it bounced. And if we were using the original backboard as the location to compute the bounces and the angles, it would actually go like this. This will cause many of the shots to miss or to at least go into the wrong spot. It creates a actually chicken and egg situation because I need the shape of the backboard in order to calculate where the ball goes, but I need to calculate where the ball goes in order to calculate this backboard shape. So it's kind of nasty. What I did this once and I calculated the backboard, which still wasn't right. Then I used that backboard as my backboard and reran the simulation. What ends up happening is you get a slightly different backboard, which is closer to correct. Then you can do it again and you get a backboard that's less different, but still different. And then eventually it converges. So that's really all there is to it. Then you just have to export it in some format that you can generate toolpaths for a CNC from. In my case, I exported an STL. I just converted it into a bunch of triangles and saved that. And then I generated the toolpaths in Fusion 360. So here's the code for my program that computed the backboard. I'm definitely not going to go through it, so don't leave. I just wanted to let you at least lay eyes on it. This was most of the work for getting this done, and it'd be a shame if I didn't show it off a little bit. And it's a good bit of code. So it does pretty much everything that I described. It selects all the locations, it does the shooting. This code here is the stuff that computes the rebound light angle. Probably the most interesting thing is actually running it. So this is one single shot, so the player is invisible. The blue is the computed backboard that we would need. And this is what the shot would do if it hits the upper right corner, and then the red square is the original backboard. So let's see if I can hack something in here really fast. So this is kind of funny. This is every 16th shot from one position in a very narrow speed range. And remember, the test is all the positions at all the speeds and all the angles, at least the ones that hit the backboard. This thing simulated a ton of shots. If this was a group of nerds, I could really go through the code blow by blow, but I think even in that case, it would still be really boring. Something about code, I don't think I've ever seen a video that's actually looking at software code that was enjoyable. All right, and if you run my funny little program, this is what it spits out. And you can ignore the fact that it's on this big block of material. That was just how I made it. We're only concerned with this top surface, so it just doesn't matter. And so I'm in Fusion 360, and I need to take this mesh that I made and convert it into toolpaths so I can machine it on my CNC machine. So the first thing that I did is I cut the mesh in half because it's symmetric and it's a lot easier to work with only half of it. It means I have to make half as many toolpaths and I can just mirror them. The way I went about making the toolpaths for this was really specific to the way that I decided to make it. I don't have a block of wood or metal that I can machine this whole thing out of. And so I decided to make it out of 2x4s. They're cheap and I have plenty of them. And what I did is I found an arrangement that would completely cover the surface that I need to machine with the minimum number of 2x4s. These are actually a little bit thicker than a 2x4. They're actually 2 inches thick. So there's just a piece of plywood that's gonna be glued to them. What I will do is I'll machine each of these individually as their own setup down to the surface. And then I'll assemble them into the final thing. So if we hide the mesh, this is the general structure here. And then this will be screwed onto a piece of wood or something. So if we look at the toolpath side of this, here's one of the planks that needs to be machined. This is treated as its own setup. And so this will be square in the machine and machined basically just in situ. And the way that the toolpaths are set up is it's just like any other part, there's some clearing and some profiling. There's a little bit of extra machining because these aren't square, and so they need to mate with each other tightly. And so that's just an extra operation that I'm gonna do. And the way that I achieved the mirroring for a given set of toolpaths, for example, this plank next to it, there's the toolpaths for this side, and then they're just inside of a mirror pattern which mirrors them in the same coordinate system. So you can literally machine a plank, take it out, put another plank in, and then machine the mirror. You don't have to touch anything, basically, and it works. So it's very convenient. I think that's all there really is to say about that. So let's make it. So I'm at the Tormach and getting ready to cut some wood. You're probably expecting me to cut some steel or something hard for the next thing on the Tormach, but nah, soft pine. It may be pine, but I am removing a lot of material. And so in the hopes of keeping at least a good bit of the sawdust contained, I built this box really quickly. And then this board here is a reference. So what I'll do is I'll machine it square with the machine. And then every piece I put in, I can just push up against it and I don't have to zero out its rotation. It'll just be square. So I'm just using some 2x4s glued to some scrap lumber to get me a 2-inch blank. And I've got 8 of these that I need to machine out. The setup's really simple. You just push it up against the reference, clamp down with some toe clamps, and go to town. I'm pretty sure this is the only time I've ever used an edge finder on wood. I wasn't even sure if it was gonna work. So I was feeling pretty pumped about this box. It really seemed like it was keeping most of the chips in. And then the machine got to 10,000 RPMs and yeah, it was a whole different story. All the machinists are gonna laugh at me, but it was awesome seeing it take these aggressive 1-inch depth of cut passes. I know it's soft pine, but it didn't stop me from feeling like I was the titan of CNC himself. There really isn't a whole lot else to say. It is just machining pine after all. I was running the machine as fast as I could, 10,000 RPMs and 300 inches per minute. It was definitely cruising. I was wrong about the box. It definitely did capture an enormous amount of wood chips. You just repeat it 8 times and you get 8 really funny looking pieces of wood that you have to figure out how to assemble into a backboard. I managed to not accidentally turn the coolant on the whole time, which is great. I also just went ahead and CNC'd these. These are oddball mounts that all the pieces sit on. I probably could have done these by hand, but they have these weird angles and it's pretty nice. You have 4 of exactly the same thing when you do it in a CNC. I've never actually cut a 2x4 in a CNC before, so this is a first. There's some extra material that I have to remove, and that's not interesting. I just have to slice it off in the chop saw. So I'm gonna get that done real fast, and we'll see how it fits up. They were all a little bit too thick, so I took the thickness down in the joiner, and I removed all my markings for which the pieces were and what orientation they were in. And I spent probably a good hour trying to back out which piece is which from the toolpaths, doing basically a CSI, which bullet came from which gun analysis. Let's do a test fit on the stand to see how they line up. Oh, wow. That fit is really good. This gap is known. I couldn't get it to fit without this gap, so what I plan to do is machine a little wedge of wood and put it in there, or ignore it. I'll probably end up ignoring it. That's typical. This looks incredibly cool. The big question is if it actually bounces the ball the way that it's supposed to. In the regions where I cut all the way through to the scrap board, you can see this circle that's transitioning from the 2x4 to the piece of scrap. Because the scrap is narrower, there's a gap. It was a mad dash to get this all laid up and machined, so I didn't really think about that. I'll probably just fill them. They also shouldn't really have any functional impact, it's just how it looks. I was thinking about how I might fill in these big gaps and cracks, and I realized I have a can of great stuff which is designed to fill gaps and cracks. So that sounds perfect. I'm gonna inject it in here, it'll all foam out, and then I'll just sand it down. I'm just hanging it on my French cleat. It's very convenient and looks pretty cool. So let's try it out. I can't wait to see this thing work its magic. What? Why? So for some reason, it looks like this backboard, instead of always making the ball go in, basically always bricks my shot. It seems like it's always hitting the front of the rim. I gotta see what's up with that. On the plus side, it does look like it's directing the ball to the rim the way that I want it to. It's just not exactly the way that I want it to because I need to go into the hole. I just realized that I have a pretty big error in my computation. And the error is that I'm not accounting for the radius of the ball. Basically, the calculation I'm doing is I'm looking at where the ball hits the wall and then the trajectory that it will follow according to whatever angle the backboard location's at, and then where it lands. And the distance that I'm computing the ball going is from the backboard surface to wherever it lands, but the ball stops here, the center stops here. Basically, the net effect of this is that I brick every shot because it directs it into the rim, the front of the rim, because the ball's 2 or 3 inches further away than it needs to be. For the moment, I can patch this just by estimating the size of the ball, so it's about 5 inches. If I move the hoop forward 2.5 inches, which is the radius, it should correct the issue, but I would rather have it be the right shape to go in with the hoop nominally where it should be. But let's give this a try. Okay, the hoop has been moved out by about the radius of the ball, and this will hopefully fix the nothing but brick problem that I was having. That's more like it. You can tell I'm really good at sports by how I throw the ball. But it's actually really hard to not aim at the center of the hoop. I've been trained my entire life to throw it at the center. This thing actually works. The only thing that I wish it did is properly direct shots from the corners. And the reason that it can't is that the algorithm that I was using didn't account for the fact that they would hit the rim. I actually had an alternative approach that would, if you were in these sort of lower quadrants, it would opt to redirect the ball up and down on a parabolic arc, so that it would go up and over the rim. I didn't want to do that for the whole rim because I'd hit up here and it would shoot it up and then it'd go in the thing, which makes for a ridiculously shaped backboard, and that's not how I want it to work. I want it to just go line drive in for all cases that it can. So I wanted to take the result that I have here and then merge it with the result in the corners where it will bounce it up. But I was having a difficult time merging those together in a way that made sense. I think I might know a way to do it, but I already made this. I'm really tempted to give it another go and maybe make another one. I might. I'm still thinking about it. It's a lot of wood to machine to get to this point. But overall, it's a neat thing. I'm gonna get it painted just so that it looks like an actual backboard and not a weird wooden slab. Waiting for paint to dry is traditionally a pretty boring activity. And so I decided to spice things up by making a better mount for the hoop. And it's just a simple little bracket I'm going to bend and then spot weld. I just about painted myself into a corner with this part because there's not enough clearance under the dies to do these inner bends. But thankfully I can just sneak the part in right about here. The power of a good bender in the pen plotter. This part has holes that are 3 bends apart and they line up. I think this is a first for me. Usually I design parts like this and the holes don't line up, and I wonder why. So I think I'd call this a success. I made a hoop that always goes in, and by always goes in, I mean goes in more often than it did Otherwise, there's only a couple things that I'd really do differently. The first is that I would change the calculation to be right so I don't have this big old protuberous. It really makes it not a regulation hoop, although I guess it's not really regulation anyway, but this bugs me. Otherwise, it's pretty cool. It was a neat construction technique. After going through this, I think there's another way that I would do it if I did it again. I'd probably actually glue up all the 2x4s into one brick that's rotated and then just machine that in 2 setups. Then I could avoid a lot of these gaps, and the construction wasn't too bad, but I think that would be easier. But otherwise, it's really cool. It makes a great addition to my French cleat. I don't think anyone else has a paraboloid always goes in backboard hanging on their French cleats, so it makes me unique and special in a way. And I know this was a pretty different video. I focused a lot more on computation and how to calculate some strange things. Hopefully you liked it. If you did, let me know. If you didn't, also let me know, because I don't want to make things that people don't like. I'm really trying to update what I show and what I focus on based on what people like. A lot of the stuff that I think is boring, people think is really cool. So just let me know. I'm happy to show anything. If you like what you see, you should subscribe. It's a really great way to show me that you like what you see. And it's also a great way to let other people see that, hey, maybe there's something cool here. And I think that's all I have for now. Thanks.